Welcome everyone, and thanks for joining DoubleRadius as we host KP Performance for today's webinar on maximizing ROI with high performance antennas. I'll begin by introducing our presenter for today. Justin Pollock is a senior antenna engineer at KP Performance Antennas and Radio Waves, where he oversees product development. And for a little more on Justin's background, he received his PhD in electrical engineering and has authored technical articles on RF and microwave engineering, antennas, physics, and optics. Before I turn it over to Justin, I'll just mention a couple quick items. Throughout the webinar, if you have any questions on the material, please enter them into the questions box so we can come back around to them at the end of the webinar. And when the Q&A is over at the end, if you could just please complete the survey that will pop up on your screen, and that would be very much appreciated. And with that, I'll turn it right over to Justin and get us started.
Perfect, thank you, Chad. So let's just get right into it. So today I'm going to be talking about a lot of KP antennas. We're going to do hopefully a little bit of education for some people. Let's see, why is this not moving? There we go. All right, so we're going to talk about some antenna principles. We're going to compare the horn and the sector antennas either quickly or slowly, will depend what mood I'm in, and talk about some of our new products, and then how do you pair a radio with a sector, or let's say you have a radio, which sector should you be choosing? So let's just get right into it. So antennas, very complex things, but we use them every day. The last point between the radio and on the AP side and this SM side. But what makes an antenna? There's all the electrical properties. First thing you look at is usually frequency. Does it match the frequency of my radio? And then you can start looking into gain and patterns, beam width. But we have to take into account all these other different properties that I'm showing here on the screen and think which ones are more important to me, which ones do I care about in my network. And it's not just electrical, it's mechanical. How big is the antenna? What does it look like? What type of wind loading does it have? Ingress protection. Most antennas typically aren't ingress protected because they have a drain hole in them. But there definitely is some versions that are. And then type of connectors. Connector type is very important because you want to make sure you have the right cable that goes with that antenna and radio. So without further ado, let's talk about antenna. What makes an antenna? It's its pattern. And by pattern, I mean, how does it spatially distribute power in 3 dimensions? So here I'm just showing a sector antenna. It's just a standard sector antenna. And what this colorful little plot in front of it, that's the actual radiation pattern of the antenna in a 3-dimensional representation. You can actually see that it's very broad in the azimuth. That's why I call it sector, and then narrow in the elevation, which gives us its high gain. If we start taking 2-dimensional cuts of this 3D pattern, we're going to see something we're used to, which are called polar plots. So here is the azimuth pattern, and here I'm just highlighting the 3 dB roll-off. So that's where half the power of this antenna is contained within this arc. And there's some other important things to look at too. So let's say you have a multi-port antenna. You can have an effect that happens called a pattern squint or pattern skew. And what that means really is that even though your antenna or sector is pointed forward, the beam actually points a little bit to the left or right in the azimuth direction. So it's usually only a few degrees, less than 5. In severe cases, it can be 10 to 15. But you need to know that because it's going to show you, like in the real world, when you're doing the coverage, you're going to see that little bit of asymmetry in the coverage on the ground. Now, if we take the other cut in the vertical direction, we have it's called the elevation pattern. So that's along the length of the sector antenna, and we can see this is actually where we get the high gain from a sector, because we narrow our beam width in the elevation so much that we squeeze all that power into that little beam right there. So that's our 3 dB beam width. This is about 7 degrees, and it gives us that nice high gain. So another features to note here are let's just start with electrical down tilt. So without putting any mechanical down tilt on the brackets, we can build antennas such that they have a fixed or variable electrical down tilt built in, such that the beam actually points downwards without pointing it physically down. KP antennas, some of them, 3 gig antennas, some of the 2 gig antennas come with 3.5 to 4 degrees of down tilt built into them. And then another thing is the upper side lobe levels. So you want to suppress these as much as you can, because these causes interference with, let's say, another tower that's 5 miles away. They're going to start talking due to this lobe right here. So if you suppress these down, less than 10, 15 dB, you usually can get away with any self-interference issue. The last thing to note here is the null filling. So that's always right below the main beam. You get this effect happens where the pattern drops very, very sharply to very low values, let's say minus 20, minus 30 dB, and then it shoots back up again. That's the first lower side lobe. And if you can somehow fill in that null where it goes very deep and fill it into maybe minus 15, minus 10, you end up be able to provide better coverage close to the tower within the first couple hundred yards. Which is beneficial if you're seeing a very weak signal in that area. Now, this is how we measure antenna. It's an anechoic chamber. All these absorber cones absorbs energy, so you get no reflections. It's fully shielded. It's a waveguide probe, and then this antenna here rotates around this center pole right here. It's a very, very robust system to measure the antennas. Now, gain is king, gain is everything. And what does that mean though? Gain is actually a term it's relative to a quantity called directivity. So before I get into directivity, let's just talk about what is, how does the antenna, not how, but what happens when you focus power. So if you have an isotropic point source, so imagine you have a charge or something that is able to radiate equally in all directions, that means you have a isotropic source or isotropic pattern, and you have a 0 dBi gain. But what happens is when you start to put some type of metal around it, or you start directing the power one direction, you introduce directivity. So but the fact that you're focusing power means that you increase the directivity on the antenna, so now it's directively pointing in one direction. So this, I'm showing an example of a 10 dBi directivity. Now, we're not at gain just yet. Once gain is actually directivity with loss. Loss comes from your choices of materials in the antenna. It comes from your reflection at the port, so your VSWR. There's lots of different sources of loss in the antenna, but what does loss do? It decreases the directivity. And I'm gonna have to use that button. And you see what you see in the real world is the gain value, which is actually less than directivity. Here I'm showing a 50% efficiency, which is a 3 dBi loss, 3 dB loss in the gain. So this actually has a 7 dBi gain. Now, there's different ways you can calculate gain. You can, take it from the spec sheet. You can actually take it from the size of the antenna and the frequency and just back of the hand calculate it, or the beam widths of the antenna. So the azimuth and elevation beam width, you use this handy formula, and you can get roughly what you think the gain should be based off of these two parameters. So there's different ways we can determine it, but gain it's a lot. Sometimes on a data sheet, you're not too sure what they're actually reporting. It says gain, but they actually might be reporting something called directivity or directive gain, which is really, like I said, it doesn't take into account the loss. So you don't actually see that in the field. And that's why you sometimes see discrepancies between what you see in the field and your RF propagation maps. Maybe it looks a little bit hotter in your coverage maps than you actually see in the field, and that's probably one of the reasons could be due to this mismatch between what is reported on the data sheet and what's actually the antenna is doing. So this is how you truly measure the antenna of a gain. Use a NIST calibrated standard gain horn. So we know the gain of the horn, and we can determine from that the gain of an antenna. Now, another kind of a very important note to it when you're looking at antenna specs is the front to back ratio. Front to back means how much power is going backwards versus forward. So here, when everything's on the polar plot is normalized to 0 dB, we can see here that if we define front to back as just the angles at zero, difference between the gain at 0 degrees versus the gain at 180 degrees, the front to back is minus 40. But that's not the best definition, because you have an actual sector behind here. You wanted to use two sectors back to back, you should be looking at front to back in terms of the or the maximum amount of power going backwards over the range of angles you're using that other sector. So if these are 60-degree sectors, you actually care about the front to back over this range of angles here. So this is how KP defines its front to back. It's at 180 plus or minus 30 degrees. We take the max value of this green curve, And you can see here that the front to back reduced from -40 to -33. But this is, even though it looks worse on the data sheet, it's more realistic in what you're actually going to care about when you're trying to do some type of frequency reuse and trying to avoid interfering with yourself. Cross pole, it's a little bit hard to understand, but it's something that happens away from the antenna. The antenna will generate a polarization called your copolarization and your cross polarization. Your copolarization is the one you want to radiate. So let's say you excite the vertical port, you want to radiate vertical polarization, but just due to what, physics, asymmetry, what ends up happening is you end up exciting the horizontal polarization just a little bit, not very much, but enough that it shows up on this plot, and this is, the resulting cross pole levels, the red curve. Now, what we care about here is called cross pole discrimination, which is the difference between the green and red curve. So if I take this at just 0 degrees, it looks very good. It's 32 dB. That's X pole, cross pole. But if we actually care about, what's the cross pole over the sector that I'm using this in? It's a 65 degree sector. So you actually look at what is the max value of the cross pole, or the difference between copole and cross pole across this entire range of angles. And you can see it's actually -18 dB. It's not as impressive as it was before, but this is more realistic. In the field, you can get away with about 10 dB cross pole. You're going to be fine, even less. You just need to be able to discriminate between the copole and cross pole. That your MIMO radio, that's what it needs to know the difference between the two, so it can send information on one and not have to worry about mixing it with information on the other polarization. Now, what is polarization? Like I said, it's well, I didn't say this yet, but it's really the direction that the electric field is polarized. So in H, and it's always referenced with the ground. So the parallel to the ground, that's horizontal, and then perpendicular to the ground is vertical. So here we show a horizontal vertical polarization. Here's a ±45 slant. It's actually slanted with respect to what we saw in the horizontal vertical. A lot of the KP antennas in our ProLine are actually in 45 slant. And the reason we do that is because it gives you such nice symmetry between each polarization. So -45 pattern looks exactly like +45. When you go in horizontal vertical, a lot of the time what happens is one of the polarization is more broader, higher beam width than the vertical, than the other polarization. So you get this asymmetry, which you actually see in the field due to a chain imbalance. This chain imbalance is not only just due to the antenna, it's actually due to how the waves propagate in your environment. So when a horizontal wave will reflect a little bit differently than a vertical wave off a tree, and what does that do is it causes the wave to maybe decays a little bit faster on the one polarization versus the other. So you see this large chain imbalance in some cases. So to minimize that, you go use ±45 slant. It's what I would say all the carriers are using this polarization scheme because they found out years ago that this gives you the nicest, cleanest signal when you have multipathing going on, so non-line of sight. Now, whatever happens if you have a horizontal vertical AP sector and a 45 slant CPE sector, well, theory tells us that you should see maximum a 3 dB loss, due to the mismatch. But that's not going to happen in the field because of all this multipathing, reflection, and just the way the wave propagates, even not in line of sight. You're not going to see this 3 dB. I think the most we've been seeing so far, and we have a lot of different customers who are doing this, is between 0.5 dB to 1 dB mismatch. And it's not that significant. And a lot of the time, the gain of the antenna will overcome this because it's such a higher gain antenna, just due to the how well designed it is. So there's some technologies which actually remove this mismatch. Mimosa's MIMO technology, its beam shaping technology, actually doesn't even care what polarization you use on both sides. They have this little white paper here down at the link, which kind of explains it nicely with some fancy math. But in any case, it's not the end of the world. Now, what is a sector antenna? A sector antenna, it's really constructed from multiple antenna elements stacked vertically in the vertical direction. So you can use 1, 2, 4, 8. 8 is about typical. We use 16 elements in some of our 5 gig 90 degree sectors, just because it gets you such nice high gain, because even though you're broadening the beam width so much in the azimuth direction. So it's just a nice little fancy animation, which kind of shows that the gain does increase just by making the antenna bigger. size makes gain. Now, I'm just going to divert a little bit and just talk about the horn antenna and sector antenna. I'm not that, I mean, the horn antenna is a great products, and they have a certain application though, and we need to understand what's the differences between a horn and sector antenna. I can see some of my images got downsampled. I'll have to fix that later. But in any case, a sector is long, rectangular, where a horn is circular, elliptical. You know, an asymmetric horn is elliptical, or there's these rectangular horns that are you know, longer in the vertical direction as opposed to the horizontal. What does that mean though? Is, you know, so sector has high gain because it narrows the elevation beam width so much, but the horn has equal or nearly equal azimuth and elevation beam widths, which causes the gain to actually be less than a sector antenna. I mean, you can see it. A horn is not as big as a sector, so you don't get as much gain. Now, one little trick that's been performed is to make it look like it has higher gain, at least in my opinion, is how the definition of beam width is defined. So with the sector antenna, the beam width is always 3 dB roll off. So if I have a 65-degree beam width, that's the 3 dB beam width. But with the horn, it's 6 dB, so 1/4 of the power is going to be referenced here, not 1/2. So it ends up being making it a little bit hard to compare a 60-degree sector and a 60-degree horn, because a 60-degree horn actually has a narrower 3 dB beam width, somewhere around 45. And I'm going to show you what that looks like. Right here, we're going to look at the sector versus symmetric horn, and we're comparing the our 4-port 45-degree sector versus a 40-degree horn and a 60-degree horn. Now let's look at the picture on the left. This is a polar plot. And you can see here that the KP sector has very similar beam width, 3 dB beam width, which is where it intersects this dash line right here, as the 60-degree horn. And if I go down to here, we can actually see the beam width, which is listed in this column. It's very close to the 60-degree horn. So that's pretty much what we should be comparing against. I mean, we can compare against the 40-degree horn, but it's such a narrower azimuth beam width that it's not a very fair comparison. But in any case, if we go here, let's just stick here on the left and just talk about the side lobes. You can see our side lobes of the 45-degree sectors is actually very nice, much better than the 60-degree horn. We can't really compare to a 40-degree horn because it's, like I said, smaller beam width. But in any case, very good front to back. If I look at the front to back ratio, we're on par with both horns and better than the 60-degree horn, which you're comparing to. Now, what does that mean though? I mean, sorry, the gain. Let's look at the gain here. The sector, because you know it's so much bigger, that means you get a lot higher gain. So we can see here that the gain over the 60-degree horn is 20.5 versus 13.2. Oops. Apologize. And then over the 40-degree horn, we're still doing better. Even though it's a narrower azimuth beam width, we're still doing about 4 dBi better. And if you look at where you're using this over a 45-degree arc for coverage, the gain is still much better also at the 3 dB roll-offs. It's a 7 dB gain improvement over the horn. So what is that going to do when you're on the ground in the field? It translates to covering more distance. So here we're looking at just some RF propagation maps in very flat farmland terrain of what it looks like for the comparison between a horn and a sector. And you see just the horns reaching out much farther. I'm sorry, the sector's reaching out much farther. And also the side lobes, of course, the 40-degree looks a little bit tighter, but the 60 degrees are pretty much on par with the sector. You're not seeing much backscattering in the back direction or on the 90 degrees along this road here. Same with the horn. So it's very similar patterns to the comparable horn, the 60-degree, but you're reaching much farther. So the moral of the story here is that if you need to get large distances, you're better off with the sector. But if you only care about very close to the tower, maybe first few miles, then the horn might work out for you. But the caveat is that you might see, well, you definitely will see a lower signal strength. The only way the horn makes up for it is by blocking out some type of external noise that's coming from a direction that's perpendicular outside of your coverage area. You're not going to be able to block out noise inside your coverage area because that's where you're serving. But if you have noise coming along this road, the horn might be able to do a little bit better than a sector. especially this 40-degree horn. I did the same comparison with the 60-degree sector and the 90-degree horn. It's the same story over again. I'll just keep it here for a bit so you can review it on your own with the recorded slides. But very similar patterns to the comparable 90-degree horn, which has the same beam width as the sector. But the gain is just so much better on the sector. And the front to back is also much better too, 3 dB better on average. So here's another study performed by Mimosa, where they compare a horn antenna, a 60-degree horn versus a sector antenna. You can see that the coverage is that much different. I mean, you're getting a wide range of coverage. Now, like I said, I don't want it to get all up against the horns. The horns are a good product for a certain application. They're, you know, a tool in your tool belt, but we just need to know when to use them. And in what cases is it best to just go up to a sector antenna. So here's just one more study. Another benefit with the sector antennas is you can get multiple ports in a single sector antenna with one mounting point, or at least one set of brackets. So we can do a 4x4, so 4 ports, or 8x8, 8 ports. And all on one mounting point. So if you're renting that tower location, you don't have to increase your rent just because you need to mount more antennas. No, you can just mount one sector antenna and be on your way. Another thing, like I said, is the higher gain. But one thing I didn't really talk about yet is the roll-off and the elevation pattern. So because the elevation is so narrow on the sector, you can actually avoid self-interfering with yourself much more easier than with the horn, where at the horn you really got to down tilt it a lot before you won't be interfering with that other tower a few miles away. Now, with the release of the asymmetric horns, it's only natural we do this study a little bit more further. So here we're looking at a 45-degree sector with and this label here is wrong. And this is supposed to be a 60-degree asymmetric horn, but and like I said, because we're comparing our 45-degree sector to a 60-degree horn, which the label here is right, because down at the bottom, because the beam widths, 3 dB beam widths are the same. The 6 dB beam widths are the same, but the elevation beam width is different on the horn, on the sector and the horn. So the sector is very narrow beam, which gets us nice high gain. And, you know, 4 dBi increase over the asymmetric horn, even though the point of doing the asymmetry is to, you know, increase gain, but you're not reaching the gain of a sector, even though the size is very comparable now. It's funny because these asymmetric horns are really long, and you're pretty much trying to reproduce a pattern of a sector antenna at this point, but at the same time, you're not getting much. I mean, the front to back degrades so much from the symmetric horns. We went from the equivalent here of this for the symmetric horn is 30-something dB, 32. They go down to 27, where for the KP sector, this one's really well designed, by the way. The front to back is 40 dBi. You're not going to have any interference issues with this sector. You can bring them nice and close together. You're doing back to back with 2 of these. And you can see here, just looking at raw gain pattern, linear plots, the sector is doing much better over the entire coverage area that you want. And also the patterns are very similar too. I mean, we can see that we're doing much better on the side lobes at this range of angles. Maybe we're failing a little bit here versus the horn, but we're good on the front to back. So you're going to be able to do some neat things with this sector antenna. I did the same study for the 60-degree. And it's just a repeat of what I said before, but now we can see here, if I compare the KP sector versus a 90-degree horn, that's the true comparison because the beam widths are the same, approximately same. We can see that the patterns are almost identical. Look at the red and green curve; they're almost identical. Maybe a little difference here at high angles, but the front to back, we're at 35 degree with the sector versus 30 degrees with the horn. I mean, we just have to be very careful in how we choose the antenna for your application. There might be applications where these type of horns are useful, but I think in 95% of the cases, a sector is going to give you much better results. And here's just a study comparing how far out you get the 60 degrees getting comparable to the 65-degree sector, but the 60 degree, it's all really focused because this 60 degree, remember, is reference to the 6 dB roll off. This is the 6 dB beam with the 60 degrees. So it's really focused, that beam. You're gonna get, this will work nicely if you have some, like I said, interference coming out from outside of your coverage area. But if you have interference inside the coverage area, it's not gonna be helping that much, and your center is gonna be just about the same. Well, it would actually be worse than the sector because the sector is coming at a little higher gain, a little hotter. So you can see here that yeah, there's definitely an improvement in how far you can get out with the asymmetric horns over the asymmetric, but you're still not getting to a sector. Now that's all I'm going to talk about horns. It's over. We're going to talk about new products now. So this is a very exciting product we have coming out around the Q1 2020 time frame. It's not late Q1, it'll be early Q1, but it's a 4-port pseudo OMNI, and I really should drop the pseudo part because it confuses even me. But really, it's an OMNI in which we take 4 ports, and it's really 2 bidirectional antennas inside of a single casing, and these patterns combine up with the EPMP 3000 radio. By the way, this is for the 3000 radio from Cambium, and these patterns combine up to give you this omnidirectional pattern. So you're able to get multi-user MIMO performance with an OMNI antenna, and that's pretty amazing. So you can maximize your coverage area. And just have one radio, one antenna, get about 3-4 miles out, maybe 5. We've done some field testing with a few clients. They by the way, it doesn't come painted like this. This is what the client did. It comes white, and the client painted it a camo. And just have one antenna, get that multi-user MIMO, so you can get that fast throughput to your high dollar value clients. So this client here, this guy here was serving some multi-million-dollar homes in this area with this one antenna over a certain 3 or 4 mile radius, and he said he was just loving this product. So he was very thrilled that he got to demo it. It's still up right now. Now there's some people got a little bit confused because we announced that product at the Wispapalooza show, and at the same time we released another similar product, but different. This is another 4-port OMNI, 5 gigahertz, but this is constructed a little bit different. So you can see it's taller, thinner, and the reason is we took 2 5 gigahertz OMNIs and stacked them vertically in the same radome. So this OMNI is going to work with either 2 2-port radios, some Ubiquiti equipment, some Cambium 2000s, or it's going to work for 1 4-port radio, but not for multi-user MIMO. So I just want to repeat, this SKU right here, 5Q OMNI-13, will not work for multi-user MIMO, but you can use it with the Mimosa equipment, any 2-port, 2 2-port 5 gig radios, or one 4-port 5 gig radio. But MU-MIMO will not be possible. It also has horizontal vertical polarization. So this is a product that's available today, right now, and you can if you're using 2 radios, you put them each on a different band so they don't interfere with each other. Here's another set of products we released, and some of them are available in stock today, is our 11 gigahertz ProLine parabolic antennas. So we created a 2-foot and a 3-foot version of these antennas, one that works with the 11FX from Ubiquiti, the airFiber, and then another one that works with the Mimosa B11 here on the right. So the 11FXs are available now, and contact us about these other antennas, the Mimosa version of the 2-foot and 3-foot. They're very well constructed. They're pre-assembled here at the factory. I'm actually here this week visiting and doing some technical work, and just very well made antennas. These guys have been doing, we've been doing this for many years. So not these specific antennas, but other variations, and they're fully pre-assembled. Like I said, simplifies your install. You just pull the 2-foot, so you pull it out of the box, you put on the mounts, and that's it. You put it on the tower right there. You're not assembling shrouds, you're not assembling radomes. The 3-foot's the same thing, but you're in a crate this time, and which really protects the antenna. It will work, you don't have to worry about it getting damaged to your site. You just drop it off at the site on the crate, and your guys goes and installs it for you. So one thing we like to advertise is, fastest time to tower. That's really important to people who are contracting out this type of installs. So we're really excited about these antennas, and like I said, contact DoubleRadius to find out what is available now and when the other ones will be available. Some dual band omnis, these are in stock today. These are great products. What we did was we kind of similar to what I said with that 5 gig 4-port Omni where it's vertically stacked. We did the same thing, but we did the 2 different bands, unlicensed bands, and all 3 combinations. So 2 gig 3 gig, 2 gig 5 gig, and 3 gig 5 gig. You're going to get at least 10 to 12 dBi gain. They're a little bit taller, of course, 66 inches, but we have guys using them right now. They love them. They pulled some of their old equipment, single band Omni. They put one of these up. Now they put 2 radios on there, and they're able to get, serve a number of different clients with using different technologies with one antenna. So here's just some, we do a lot of client testing. And this is a client that put up our Omni right here. Ignore these other antennas, but he replaced his 2 gig Omni, and then he with this one, so he added the extra 5 gig band or 3 gig band on top of it, and he saw pretty much the same gain as he saw, plus or minus 2 dB of what he saw with the previous Omni. Same here with the 2.5 Omni. Watch Communications did this testing for us, and they replaced their 2 gig and then the 5 gig Omni. And they put up this one, and they were able to see, within 1 dB, the same signal strength. And both clients are very happy with these antennas right now. They're still up in the air. This is just some field testing. I'll just leave it here so you can browse it on your own after. But really, like I said, this is actual raw data results in which we could see that the signal strength is roughly maintained going from before 2 gig Omni to the new dual band Omni, -70 received to -68. Now let's just go looking over the modulation. The data rate is staying roughly the same. It actually improved here on the receive side. Improved here. I mean, you're going to be able to get your same modulation rate as you saw with a single band Omni. This is a really great product. It's called the Bazooka or the 900 megahertz Dual-Pol OMNI. So this works great for maybe your Cambium PMP 450i radio or any really 900 megahertz radio you got. I have to fix a typo here because we found out, originally we designed this antenna just for 824 to 928, but we found it actually supports the entire 800 to 1000 megahertz band. But this is where we optimize it, and truly we optimize it for the unlicensed 900, so 902 to 928. But it's 2 ports, 45 slant polarization, very, very well-designed antenna, minimum azimuth ripple. So what does ripple mean? Oh, by the way, this is a little trick, guys. So if you have an Omni up in the tower, no Omni is a true Omni, especially a dual pole. They always, just due to the physical asymmetries of them, they don't have a perfectly omnidirectional pattern. What best you can hope for is to minimize the ripple or circularity, as what we call it. So you want it to be as Omni-like as you can. Never can happen. So if you have a field issue where you have an Omni up in the tower, and it's not giving you the signal strength you want, try just rotating it a little bit. And the act of rotating it will cause some of the signal, maybe the hot spot in that signal to kind of move to where you want it to be. And you can rotate it such that you rotate the dead zone. It's not really a dead zone, but I'm just using that terminology to be somewhere where you don't have clients, or you're not trying to pick up clients farther away. So this is great if you want to, penetrate dense foliage with that 900 megahertz band. So we did some great field testing. Here's rural Ohio, farmland, tree lines, ravines. We did some comparisons against a competitor. There's only one out there, so I'm just going to leave it as competitor A, and then the KP Omni. And then we looked at the delta, and we saw just a massive increase in gain in some clients, and then a little decrease in one. But in reality, this antenna was still working great for them. They loved it. They were able to get out 5 dBi or 5 miles with this one antenna and serve a number of different clients. So this is a great cost-effective solution to serve many clients at 900 megahertz without having to put up 2 sectors and 2 radios. So this is the complementary 900 megahertz 120 degree dual pole sector. So let's say you started with that Omni and now you're picking up more clients, you need to get a little bit more capacity, you go put up 2 radios, you go put up 2 sectors or 3 sectors. So you use one of these, 1 or 2 or 3 of these sectors, and you're going to get out very far distances, this 12.5 dBi gain, and pick up more clients. And this is just a really excellent antenna for these type of applications. So here's a kind of, and I wish I had a fancier slide to segue into here, but our TV white space antenna solution. So we have 4 different TV white space antennas, 2 sector antennas, which I'm showing on the screen, a flat panel antenna, and a Yagi antenna. So let's just talk first about the TV white space sector antennas. So these compare with your Redline radios, your whatever radio you want to use in this space. There's more and more coming online every month. But in any case, we have a dual pole H&V version and a single polarization vertical version. In a lot of cases in this space, I wish I had a slide on this, but all your TV stations are broadcasting on that horizontal polarization. And it just puts so much noise out. So only in like certain areas, and you got to do a spectrum scan in your area. You got to find out what is the actual noise level that I expect to see, and then you can set your expectations. But if you have a lot of noise in your area, it's all on that horizontal polarization, and you can kind of mitigate that by using vertical. So you put up you want to do 2 by 2, so you put up 2 single pole vertical polarization sector antennas. And you were able to get above that noise floor and serve your customers with this spectrum. So it has a built-in GPS antenna in it, and we also have a direct mount option for the Redline RDL 3000 XP Ellipse radio. So these are also available now. And then here's the dual pole Yagi. This is a kind of a neat solution. So we took our 900 megahertz Yagi and just scaled it down in frequency we didn't want to increase the size too much, because that's one of the issues people are having on the subscriber side is the antennas are just too big. Clients are complaining, blah, blah, blah. Log periodic antenna is just too big. So we produced this nice form factor, small form factor, dual pole Yagi antenna. So you don't have to put up 2 single pole log Ps antennas and have this massive, mounting structure for them, and it sticks out 2 meters. No, you put up this antenna. It's about the same size as KP's 14 dBi 900 megahertz Yagi. Very lightweight. It's aluminum. It's very high quality too. You're not going to see rusting issues happening, corrosion, fading, and this is great for your wintry areas for you guys up north. Any ice buildup that builds on this antenna is going to melt away once the sun hits it. That black coat will heat up nicely, and the ice will build off, so you won't get that drooping on the end of the Yagi boom. Another really great thing people like about this is the adjustable polarization. So you're not fixed to H&V or plus or minus 45 slant. You can go anywhere between the two. And this is great because once you're in the field, you're going to find, like I said before, polarization never stays H&V and 45 slant once it leaves the antenna, somewhere in between. So you can rotate this, so you can maximize your center in both chains and your signal strength. And people love that flexibility. It ends up getting them, you can get up to a dB increase in your signal strength just by doing that. So yeah, this is a very popular antenna. We sell it in a 2-pack. So but it's $100 each for one. So that'd be $200 for a 2-pack. Now here's our TV white space flat panel antenna. You actually get a little bit higher gain out of this because it's a little bit bigger in terms of the horizontal vertical direction. But so this is a great little solution. We have the option to mount the radio, like I said, the Redline radio directly to the back. This works for the Gen 1 version for the SMs, for the and then for the, I think there's a Gen 2 version, which is now a smaller form factor that won't direct mount. You can just pull mount that radio, but very strong brackets. I mean, you can see here we load up the weight here and with the bracket on the back, and this antenna is not going anywhere. Very well designed. We did a lot of testing on this antenna because we had to tool up all the new components here because this is a custom radio for us. So very good weather protection, good side lobe suppression, front to back ratio. So this is gonna be a good antenna. If you're having maybe some interference issue with the Yagi, you go to the flat panel, might resolve that for you. Like I said, we did some testing. So here on the left, this is the log P antennas. You see the two of them mounted here. So that's a pretty big solution for subscriber side. And then here's the KP antenna. This is mounted, it looks like in horizontal vertical. And then here's a competitor's dual-pol panel. And then here is at least our prototype version of our dual-pol panel. A little bit bigger, right? But what we saw here was everything was compared against Redline's 11 dBi single pole Yagis, and we saw I didn't have a picture of it, but with their 11 dBi panel, they saw about the center is about the same level as the base case, which is those Yagis, which is here the picture on the right. Now, once they put in the competitor's smaller panel, they saw about a 3 dB drop in the signal strength, QAM rate dropped, and got some more latency and jitter. And then they put in the KP panel. They saw a little bit improvement over the competitors, not too much, just a little bit. And then they put in the Yagi, very similar to the panel. The gains are very similar. 9 dB is typical, but it does drop in the lower part of the band. But they were very happy with this because they were, like I said, adjust the polarization to maximize the signal strength. Now, here's ProLine parabolic dishes. Just being very, very brief, these are excellent products. We get comparisons from guys who pulled old equipment off the field and put up the KP dish, and they saw for equivalent antenna, spec sheet says the same gain. They saw a 1 to 2 dB increase in the gain, even more on some of the cheaper parabolic antennas. So very low side lobes, good pattern spec. We're very proud of these antennas. We have direct connect options for the Mimosa C5C. We're coming out shortly with one for the ISO stations. And then we have also N-type connectors. You can actually direct mount your radio to the back of this because it's a little pole right here that we made. So you can put a little hose clamp around there. Oh yeah, here we go, some pictures. Man, these got degraded, but very tough, built like a tank, we say. You're not gonna run into issue. We have an optional radome too. Very stable performance, 4.9 to 6.4. So very, very good antennas. Like I said, patterns are excellent. You're gonna not see any noise as you did with some previous antennas. So I'm just gonna, and we also have the quick connect function. So it allows you to adjust your polarization between H and V and 45 slant. It's also very easy to assemble. Once it comes out of the box, it's really 3 components you're putting together. Very, very fast. I can install one in about 2 minutes. Radio connect. Sorry, you'll have to pause the video when you go back and review if you're interested, but they're very simplified installation. We wanted to make it easy for you guys. Now here's our ProLine small angle sectors, and these are great products too. You want to provide coverage over a very small range of angles. You use this product. They're well designed compared to some of our competitors. I know that you're like, of course you're saying that, but we designed these specifically for the CBRS band at 3 gig and the unlicensed 2 gig band. And because we did that, we were able to get much better side lobes than our competitors. So check these antennas out. And this 5 gig antenna, this is a really awesome antenna. It's the front to back's amazing. The gain is very, very high, 20.5 dB, and it's not too big either. It's kind of what the patterns look like of the antenna. The side lobes are so low. I mean, they look like horns almost. And then this 45, no side lobes at all on this scale. ProLine sector, come and check out our website or go to DoubleRadius, check it out. But we have a wide range of sector antennas that cover every frequency that you would need, and also combinations, dual band sectors, 2 gig, 3 gig, 4-port, 8-port. We have mostly the slant polarization, but we did recently come out with a 2 gig, 5 gig HV polarization. So this is going to work great with some of your equipment that maybe you're having a little bit hard time justifying switching to a slant. So come and check out this antenna right now. We can also do a 4-port version on request. So please reach out and contact us on that if that is a need for you. Now, I said I was going to talk about radio combination, but it's kind of obvious, right? Like if this is an 8-port antenna here, it's got 3 gig and 5 gig on each port. You're going to want on your 3 gig side, you're going to either want to use a 3 gig 4-port radio or 3 gig, 3 gig 2-port radios, and then 5 gig, it's the same thing. So here's what you do with our 8-port sector, 3 gig, 5 gig. I'm just going to go here. This is 2 gig, 3 gig. Lots of different options you can choose from here. Lots of different options. 2 gig, 5 gig, very, very, very nice clean patterns in all the bands and all the ports. Lots of different options. I mean, Cambium, Telrad, Ubiquiti, Bicells, Mimosa, like just lots of different things you guys can do. Now, I'm just going to skip through here. I'll just leave it on here so you can take a look at your leisure later. But I wanted to talk briefly on the ROI part. Like I said, we do a lot of real world testing. You know, this is testing in Alberta in the middle of a very cold day. I don't know why they went out that day, but what we saw was in the lab, we saw the competitor puts this dash blue line up on there's patterns on the spec sheet, but this is what we measured in the field in the lab. It was about a 1 to 2 dB drop in gain, but on the spec sheet, it's comparable to what we put on our spec sheet and also what we do in our measurements. So it's kind of just shows that you got to be very careful what you see on the spec sheet and always question. What does this mean though? Once it's in the field, even though you know the KP antenna might cost a little bit more, because you're reaching farther out, you're going to be able to pick up a few more clients. Not only that, you're going to be able, on your existing clients, you're going to be able to see that increase in signal strength, maybe increase in modulation rate. You can offer them a higher package because they're getting higher throughput. So even though you may be spending a little bit more, $100, $200 more than a competitor, our competitor's antenna, you really are, you're going to see that return on your investment right away. I mean, within a month, you're going to make your money back because you're picking up more clients or charging more. So we need to take our short-term thinking and expand it a little bit longer, I think, in order to think, you know, why do I choose this antenna over our competitors? A lot of this is and this is going to be the end of my presentation, but we went and took a competitor's antenna and measured it in the lab, and we saw a very drastic decrease in what we saw the gain reported on the data sheet versus the gain in the actual gain. We can see here where most people are using the antenna at 585 gigahertz, that the gain it's a 6 dB drop. I mean here it's like a 9 dB drop. And the reason is because the side lobes on the competitors just shoots up. It's shooting half the power upwards and half the power close to the ground. You're gonna run into some issues here. This is also probably gonna fail Uni 1 spec at the 5150 to 5250 band. So it's what we saw. We actually went and mounted this antenna. This is the RF coverage plot. You can see there's this null zone here. And we actually mounted this antenna up here. This is a funny story. This tower fell over a few days later. And we saw that the signal strength of the KP antenna, which is in green here, was much greater than the competitor's antenna. And in some cases, some clients dropped off completely with the competitor antenna. And the customer's like, this is junk. I didn't chuck the antenna, but I took it back and put it away into storage. So very, very careful in how you are choosing your antenna. Even though it might cost a little bit more, you're gonna get that money back right away because you chose a higher performance antenna. So taking that in mind, I'd just like to say thank you for listening to me talk for the last 45 minutes. And Chad, I think we're ready for questions.
Okay, yeah, feel free to enter questions that you may have here if you didn't get a chance to ask those yet. We did have a question from earlier on when you were covering the horns versus the sectors and which type of antenna to use in which scenario. And the question was if a sector should be used for point-to-point.
I would avoid it as much as you can because you're better off using an equivalent like a microwave, like a backhaul dish, 1 foot dish, even a flat panel, because you want a nice directive beam. With the sector, if I go back to these plots right here, let's look at here, a sector, just look at one of these red circles. You're spreading way too much power out in directions you don't care about. This is point to point, not point to multi-point. So you're better off using a flat panel antenna or a parabolic antenna or a grid antenna or even our Yagi antennas would be a much better option for you. You want something highly directive.
Okay, can you cover the ideal scenarios for the MU-MIMO antenna?
Yeah, for sure. I mean, I can go back to it, but in any case, the ideal scenarios is you don't have a lot of clients. You can't justify putting up. You want to give clients some high value clients, a very high throughput. So you want to make sure you're using that EPMP 3000 radio, but you don't want to really justify putting up 4 radios because you want to get this omnidirectional pattern because you have all the clients scattered everywhere and you can only mount the antenna right in the middle. So that's the kind of ideal scenario where you use this MU-MIMO, this Omni antenna with the EPMP 3000. You're able to serve a lot of clients, well, not a lot, but a handful of clients with high data packages, and you can charge them a lot for it. And you want to be able to use multi-user MIMO on the uplink, so you can get that high throughput on the upside. So that's kind of ideal scenario is low density, but you want to charge them a lot of money. So that's where I would use this this type of package. Or you have a lot of clients and you want to charge them, and they have low data rates, and it's just all about investing. Like when you're starting out, you put an Omni first. And then, or if you want to get 360-degree coverage, and then once you build up the capacity and your clients, then you can justify buying another radio. But until that point comes, you start with that Omni, go to 120-degree sectors, then 90-degree sectors, 65 degrees, and if things get crazy, you go to 33 degrees, 33 or 45-degree sectors.
Okay. I think we're absorbing all the information. Are there any other questions that we would like to ask here before we end our time today? Go ahead and enter those in if anyone has them. Otherwise here, in just a moment, we will close out. I think that is it for now. The recording will be available for you to review. There is, again, a lot of information, so we will be sending a recording in the next couple days. If you could please just take a moment now as a survey pops up on your screen to go ahead and fill that out. We would appreciate it very much. And thank you again, everyone, for attending and listening in, and we'll hope to see you next time.
Perfect. Thank you, Chad. Thank you, everyone.